And also we got some advantages of high reliability, low cost, and simplicity of the installation. Next, we go to see the state observer that are used to the estimation of the variety of the real-time control systems. In an observer-based control problem, the unobservable states are estimated by using the system inputs and outputs. Very recently, the author announced studies the observer-based controller for switched nonlinear network control system under packet dropouts. Next, we go to see the event trigger strategy is an alternative to the time trigger strategy. In the event trigger strategy is a very efficient strategy for reducing the communication burden and improving the transmission efficiency. In comparison to the time trigger control, an event trigger control is an efficiency by avoiding the unnecessary communication and sending information based on the predefined criteria. Many valuable results are using event trigger control in previous published papers. In reference 4, the author developed event trigger control for network switched system with the transmission delay and packet losses. The packet losses occurs exclusively in the channel from the sensor to the controller. Another popular type of the packet loss which occurs in the link from control to the actuator has not been thoroughly investigated. The robustness and the disturbance rejection attentions also has not received such attentions. So best of my knowledge, the finite time observer-based externality control for uncertain network control system with the random packet losses and the communication delays under the event trigger scheme has not been fully investigated. This is my contribution. This contribution in observer-based event trigger control strategy is considered for uncertain network control system with random communication packet losses in the finite time interval. Random packet losses may occur simultaneously from sensor to the controller and also control to the actuator. The random packet losses are treated as a stochastic variable. Both the finite time boundedness and the finite time externality control are considered in this paper. Finally, we are given the numerical example. Now we get to the problem formation. So in this problem formation, a physical plant of the uncertain network system in figure number 1. Based on the above concern, the network control system with the disturbance signal with represent the state space equation number 3.1. Here x of t is nothing but state vector, u of t is the control, w of t the input disturbance input signal. Then y of t, z of t is denoted the measured and the control output. Here a cap and b cap are defined here. Here a to g are the real constant matrix with well known. The parameters and uncertainties are defined here. Then the uncertainty term m1, n1, n2 are defined here. The whole state of the target plan 3.1 cannot be measured directly. Therefore, the state information of the target plan 3.1 is estimated via the design of observer-based controller defined in equation number 3.2. Here x cap, y cap are the estimation of x of t and y of t. It's a very important thing is our control gains. So u bar is nothing but the control input of the observer. U cap is the control input without random packet losses. U of t is the control input of the controlled system. K and L are controller and observer gain matrices. Beta of t is nothing but a stochastic variable. Now we go to the energy constraint. The event detector consider the following condition in equation number 3.3 to decide whether the current signal should be transmitted to the controller or not. Here sigma is nothing but the known parameter, pi 1, pi 2 is nothing but symmetric positive definite matrices. E cap is nothing but the error between the two states at the latest and sampling instance. Whenever the data released by the event monitor is forwarded to the controller at Tk, it's called the communication delay. That's nothing but a sensor to controller delay. That's nothing but tau sc. Consequently, when the controller transmits the actuation signal to the actuator at Tk, the another communication delay is called the control to the actuator delay. That's a tau Ca. Therefore, the total two delays nothing but tau Tk. That is, we have the limits at 0 to tau m. Tau m is the maximum delay. The input of the control input in equation number 3.4. Now we define the error is nothing but E of t is nothing but x of t minus x cap of t. Then the closed loop system in equation number 3.5. By setting the augmented state vector this one, then the closed loop form of 3.5 with the compact form is equation number 3.6. Here pi of t is nothing but the initial function of zeta of t. The systematics are given below. The following assumptions and definitions are needed to prove the accurate result and the upcoming result. So from this assumption, nu is nothing but a positive parameter. W of t is the disturbance input signal. Then satisfy this equation. Then mu is greater than or equal to 0. Then 0, t is nothing but a fixed time. From this definition, nothing but a finite time bounded for a given time constant, finite time constant Tc and the external disturbance W of t, and satisfying the assumption 1. Then the closed loop augmented system 3.6 nothing but a finite time bounded and satisfy this equation. So in this paper, we aim to design an observer-based event trigger control for uncertain network control system 3.6 over the finite time interval, and also we satisfy the HRD performance level in equation number 3.7. Now we get to the main result. In this result, we using the two criteria. First one is a finite time boundedness, another is a finite time externality control. So in the finite time boundedness for the augmented error system 3.6, we want to derive. So by using the Lupino function 4.1 is here. PQR is nothing but a positive different matrices. From this theorem, given some k-loss and a control gain matrix, observer gain matrix, then the augmented error system 3.6 is a robustly finite time bounded. Satisfy the equation number 4.2 to 4.7, where the remaining parameters are defined here. Now we go to the proof. In this proof, the calculating derivative of the Lupino function and take the mathematical expression equation number 4.5. According to the lemma 1 in 11, for any matrix MA and satisfy equation number 4.3, we get equation number 4.6. In addition, the remaining parameter of the Lupino function equation number 4.7. Then combine all the equation along with the even trigger condition, then applying the score complement law, we get equation number 4.8. If pi is less than or equal to 0, we get equation number 4.9. By using the simple calculation, we get these equations. So if the condition 4.4 is hold, the following conditions are also satisfied. This is the complete of the theorem 4. This one. Now we go to the second theorem. Is nothing but a finite time HNT based even trigger control scheme. So in this theorem, similar to the equation number theorem 4.1, for the given some scalars, then the augmented error system, the network control system 3.6 is a robustly finite time bounded with a desired HNT performance and satisfy the following LMX. This is the parameter of the each LMX. Further, the desired controller and the observed gain matrix are calculated this one. So now we go to the proof. In this proof, according to the theorem 4.1, the augmented error system 3.6 is a finite time bounded. Now we will prove the finite time HNT performance of the closed loop augmented system 3.6 under the zero initial condition. Now by considering the same Lupino function in the theorem 4.1, the following the similar derivatives along with 3.7, we can get equation number 4.7. By using the simple calculation, we get equation number 4.8 and 4.19. By integrating the previous mentioned equation 0 to Tc, we can conclude that our closed loop augmented system is robustly finite time bounded. Now we get to the numerical section. In this section, we present a numerical example to demonstrate the effectiveness of the obtained observer-based event triggered scheme for the augmented error system 3.6. It's a finite time bounded by using the following parameters. The remaining parameters are defined here. That the external disturbance are chosen as W of t equal to this one. By solving the LMI 4.14, obtaining in 4.12, we get the MATLAB LMI toolbox, we get the feasible solution. We get the observer and the controller gain as follows, K and L. By using the initial conditions, based on the above controller and observer gain matrices, the simulators are as follows. From this figure, we can represent the state and observed response of the augmented error system 3.6. From this figure, we can represent the error and the control response of the augmented system 3.6. From this figure, the finite time bounded for augmented system 3.6. Our trajectory does not exceed the C2 values. C2 is nothing but 6.0578. This is the response for the release instant and release interval, the error and threshold values. Therefore, from this simulation result, observe that our observer-based augmented error system 3.6 is robustly finite time bounded and also satisfy the finite time HNT performance. This may from conclusion, observer-based control issue for uncertain network system by using the finite time HNT control and even trigger sampling scheme. Random packet losses may occur from sensor to controller under the control to actuator. The observer-based state feedback control was designed to ensure the uncertain network system subject to the random packet losses in the finite time interval. Finally, we get the numerical example. This is my references. Thank you so much.
Okay, so thank you, Doctor, for your presentation. So, any question here? Okay, so I also don't have question. Thank you.
Thank you so much, sir. Thank you so much.
So let's move to the third